Howdy. This video is on intermolecular forces. Physical properties of materials, melting point, boiling point, vapor pressure, viscosity, solubility, surface tension, capillary action, cohesive forces, adhesive forces are determined by intermolecular forces. Intermolecular forces are the forces between molecules. We're also going to include interactions between ions as intermolecular forces and interactions between ions and molecules as intermolecular forces. After watching this video, you should understand the importance of intermolecular forces, understand how all intermolecular forces are electrostatic interactions, be able to put the different intermolecular forces in order of increasing strength, understand how intermolecular forces affect different properties of compounds, be able to relate viscosity, surface tension, capillary action, cohesive forces, adhesive forces, and solubility to intermolecular forces. And so intramolecular forces are the forces that hold atoms together forming molecules, and so that's like covalent bonds. Intermolecular forces are forces between molecules, but also include the interactions between ions or between ions and molecules. So please don't get confused by the name. Intermolecular forces include interactions between molecules, molecules and ions and ions. Now, while the ion-ion interaction and ion dipole interaction are pretty strong, the other intermolecular forces are much weaker. And so again, intermolecular force is very important for the physical properties of materials, boiling point, melting point, vapor pressure, viscosity, surface tension, etc. And so if we look at solid benzene, and so this video is a pretty good representation of a small chunk of solid benzene. Notice that the faces of most benzenes face the edge of other benzenes. And so having edge-to-face interactions optimizes electrostatic attraction. Remember, the blue means partial positive charge, the red means partial negative charge. Because benzene has those pi electrons, the faces are partial negative and the edges are partial positive. And so this position optimizes electrostatic attraction between molecules, and that's what keeps the solid benzene. And so the stronger intermolecular forces that hold a solid together, typically the higher the melting point. Now this video is of ice. The bar represents 5 picoseconds. A picosecond is 10 to the minus 12th seconds. And so there's always motion at the atomic level, even for a solid. And so this is kind of what ice looks like at 25 or 0 degrees Celsius, I forget which. And so there's always motion. It's very, very fast motion. Again, the bar represents 5 picoseconds. Now, it's the intermolecular forces, the hydrogen bonding, that's actually holding that ice together. Now, in a solid, typically the molecules cannot move relative to each other, but you always will have some motion, some vibration. Now, this movie represents liquid water, and the dashed lines represent hydrogen bonds. Now, you still have intermolecular forces, but notice that the molecules can move relative to each other. The hydrogen bonds are being broken and being formed. And so we saw the stronger intermolecular forces, typically the higher the melting point, while also the stronger intermolecular forces, the higher the boiling point and the lower the vapor pressure. And so in general, the strong intermolecular forces, the more kinetic energy is needed to overcome the intermolecular attraction, the higher the melting point, higher the boiling point, and the lower the vapor pressure at any given temperature. Vapor pressure, all liquids will have a vapor pressure, and it's just that some molecules will escape the liquid. And the stronger the intermolecular force is, the stronger attraction, the fewer the molecules will escape the liquid, and the lower the vapor pressure. Intermolecular forces also determine solubilities. And so if two molecules have similar intermolecular forces, they'll be miscible in each other. If they have very different intermolecular forces, then they'll be immiscible. Miscible just means that you can mix them in any ratio and you'll form a homogeneous solution. Immiscible means that they won't mix no matter what the ratio is. And so carbon tetrachloride and water have very different intermolecular forces, and so they're immiscible. C6H14, which is hexane, and water have very different intermolecular forces, so they're immiscible. Carbon tetrachloride, CCl4, and hexane have very similar intermolecular forces, and so they are miscible.
Nonpolar carbon tetrachloride is poured into a test tube. When a nonpolar colored solid is added, the solid dissolves in the carbon tetrachloride. When polar water is added to the test tube, it forms a layer on top of the carbon tetrachloride.
This is what we
since
mean by
water is
immiscible.
with and less dense than carbon tetrachloride. When nonpolar hexane is added to the test tube, it forms a layer on top of the water, since hexane is immiscible with and less dense than water. When the test tube is vigorously shaken, the two nonpolar liquids form a single layer at the bottom of the test tube, and the polar water layer sits above this layer.
And so you've probably heard the phrase likes dissolve likes, and that means if you have similar intermolecular forces, they'll tend to be miscible. If the intermolecular forces are very different, they'll be immiscible. You know, a typical example is given as oil and water, and so no matter how much we shake this, the oil and water will always separate. They're immiscible, they have very different intermolecular forces.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
And so again, miscible means that liquids are soluble in each other in all proportions, like ethanol and water. Immiscible means that they're not soluble in each other, such as hexane and water. And so it's kind of interesting. Alcohols contain OH, and so the OH part looks like water. And so short-chain alcohols are actually miscible in water, but long-chain alcohols are not miscible in water.
Colored water is added to ethanol, butanol, and hexanol. Water is miscible in ethanol, but not in butanol and hexanol. Butanol has a shorter carbon chain and is less hydrophobic than hexanol. This causes butanol and water to separate more slowly.
And so on top we have ethanol. And so water looks kind of like that. Water has oxygen and two hydrogens. And so ethanol looks kind of like water. It's going to have similar intermolecular forces. And so ethanol and water are miscible. Now, even though butanol and hexanol have this OH part, which looks like water, it's got a larger part that doesn't look like water. And so this part has a different intermolecular forces. And so butanol and hexanol are immiscible, but ethanol is miscible in water. Now, it's kind of interesting if you notice, this end of hexanol is polar, and this end of hexanol is nonpolar. And so sometimes we can actually make a molecule that one end is polar, the other end is nonpolar, and that's actually referred to as a surfactant molecule. Or surfactant molecules have one end that's polar, one end that's nonpolar. And so if you look here, the red corresponds to the oxygen, and so this end is going to be polar, and then this is long chain alkane, this is nonpolar. And so if you put this molecule in water, what happens, it forms what we refer to as a micelle. And so the nonpolar part comes together, and then it's surrounded by the polar part, and then can actually dissolve in water. Now, surfactant molecules are important in detergent because if you use a surfactant, you can actually get the nonpolar part to go into the oil, and then you have the polar part on the outside of the oil, and so you can actually get oil to dissolve in water.
Surfactant molecules exist in aqueous solution as micelles, clusters of surfactant molecules. The long nonpolar chains of the surfactant molecules are pointed inward, and the polar charged end groups point outward into the water. In solution, water molecules interact with the polar negatively charged ends of the surfactant molecules and with the sodium cations that provide charge balance. When a microscopic oil particle on an item of clothing is exposed to this solution and there is agitation, the surfactant molecules become embedded in the oil droplet through the hydrophobic, oil-loving hydrocarbon chain part of the molecules. As more and more surfactant molecules become embedded in the oil droplet, it is lifted from the surface of the clothing. This process occurs because the polar, charged ends of the surfactant molecules interact strongly with the surrounding water.
It's also kind of interesting if we think about fabric softeners. Fabric softeners are used to kind of like cap those OH groups to make the fabric softer, but that actually makes the fabric less absorbent of water.
In untreated cotton, surface hydroxyl groups attract each other and make for a rough surface. Fabric softener molecules are surfactants. Their polar heads are attracted to the hydroxyl atoms, leaving their nonpolar hydrocarbon tails out. The tails, because they display weak intermolecular force, can slide past each other, thereby imparting a soft texture to the cotton. In untreated cotton, surface hydroxyl groups attract water molecules, so cotton absorbs moisture. In cotton treated with softeners, however, some hydroxyl sites are occupied, making the fabric less attractive to water and therefore less absorbent.
So again, all about intermolecular forces. So molecules in a liquid experience cohesive forces. That's the attraction of molecules in the liquid. Molecules on the surface experience less cohesive forces. Now again, these are electrostatic forces, and the stronger the electrostatic attraction, the more stable. And so the molecules on the surface are going to be less stable than the molecules in the bulk of the liquid because, again, the stronger attraction, the more stable. The weaker the attraction, the less stable. And so this is why water forms drops. A sphere is a shape that has the minimum amount of surface per unit volume. It also results in surface tension. Surface tension is just the result of the surface being as small as possible. And so that's why sometimes you'll get it goes up a little bit on top. And so again, the surface is less stable than the bulk because the surface has less cohesive forces than the bulk. Now, surface tension is also why you can float things on water because it takes a little bit of pressure to actually break through the surface.
A paper clip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paper clip sinks.
And so the surface tension's a result of intermolecular forces. Again, it's the intermolecular forces that make the molecules in the bulk of the liquid more stable than molecules on the surface. And so that's what causes surface tension because the surface is less stable. The liquid will try to take the shape that minimizes the amount of surface.
You think nothing exciting would happen, you think it would just go like this. But what we'll see is much more interesting.
All right, let's drop it.
What we've got here are water droplets, which look pretty ordinary at normal speed, but at 2,000 frames per second. Maybe mathematician John Bush can explain to us just how a drop can bounce.
Whoa, whoa, whoa. That is so cool. And that's just going to float all the way over to here. Ho!
Okay, so you're saying that happens all the time?
That's right. Every time a water drop coalesces into water, so every time it rains, a raindrop hits a puddle.
Rains. That's raindrops in a puddle.
Yeah, so that's billions of times a day. Why does the droplet sit without just connecting?
So there's an air layer in between the two, and it's basically it'll coalesce as soon as the drop makes contact with the bath, but it takes a finite amount of time for the air layer to drain.
Or for non-PhDs, there's a thin layer of air separating the drop from the water. But as the air is pushed aside, most of the droplet connects with the water below. But this happens so fast, the connection is actually pinched off, and a smaller droplet is formed. But why do some of the drops leap up into the air?
When it coalesces, waves are generated at the point of contact, and they sweep upwards, and they apply a force, which lifts the drop off the surface.
And then once again, it's surface tension. It has enough force that it pulls itself back off.
That's exactly right.
A tenth of the size.
This surface tension is the quality of a liquid that causes the surface layer of that liquid to behave like an elastic sheet. It's the effect that allows insects to walk on water and water drops to hold together.
Wow, that's crazy. That's amazing.
This cycle happens again and again until the droplet is small enough to be completely absorbed.
Try to get one.
And so again, it's all about intermolecular forces. The sphere is the shape that has the smallest amount of volume per unit, smallest amount of the area per unit volume. Because of intermolecular forces, the surface is less stable than the bulk of the liquid, and so it wants to take the shape that minimizes the amount of surface, which ends up being a sphere. And so this video was actually done on the space station, in the space station.
Okay, there. Okay, I'm going to put a puff of air in from this
And
side.
so notice that the water wants to be in a sphere to minimize the amount of surface area. And so there's very, very little gravity because obviously this is in the space station.
Cool. Wow, I just love those oscillations. Here we go. Okay. I'm going to switch it to a black background. Yeah, so that's about 800 mils. So this should put it around 1100 milliliters. Let's see what happens here. Oh, I just love that. Look at that. Amazing. Just one of these jaw-dropping moments. Okay, here we go to do it again, looking into the camera. Big puff. Here we go. Oh, right at the lens. I saved the lens. What I'm planning to do is, after this whole series of experiments, I'll suck all this water up with a syringe, I'll put it back in bags, and I'll use it to make tea with, so I'll end up drinking my experiment. You gotta conserve your resources when you're in a frontier. You don't get to see this as common, intuitive observables on Earth. And so when we go into a frontier, our normal Earth-honed intuition no longer applies. And this rule works when you go to the bottom of the ocean or into the stratosphere or wherever you find your frontier under the stage of an electron microscope. Your normal everyday life intuition no longer applies. And that's why frontiers are rich in discovery, because things aren't the normal, they aren't the usual. Joe, come take a peek at this.
Holy crap.
Get my towel ready to catch the satellite drop. Here we go. Isn't that wild?
That's great.
It's a superposition of surface waves that go around the outside of the sphere and body-centered waves, inertial waves that go through the middle. I'm going to give it another puff just because I'm in space and I can. And instead of putting a puff of air on it, I'm going to put a puff of water. This is going to have a lot more momentum in it than the air. Whoa, whoa, I was afraid. Oh, look at that, cool. I squirted water through. Oh, isn't that cool? The water in the sphere went around the air cavity and formed a huge bubble. Wow. Oh, that is so cool. Let's see what my hand looks like. Oh, look at that. Yeah, oh. There we go. Yeah, that's good. That's good. Shows that optics works. And let's see what my mug looks like. Oh. I can be a human pendulum. This shows the lens law. Motion is in the opposite direction and the image is inverted or upside down. And there I am, and I'm going to come up here with my eyeball.
So again, kind of cool. Just about intermolecular forces. The intermolecular forces make the bulk more stable than the surface, and so liquids tend to try to minimize the amount of surface. That leads to surface tension. That's why drops are spherical. That's why bugs can actually walk in water. Also, interactions between molecules causes viscosity. Viscosity is just the resistance to flow.
The viscosity of a liquid depends on the strength of its intermolecular forces. Glycerol has relatively strong intermolecular forces and is rather viscous. Its resistance to flow is high. Ethanol, by contrast, has weaker intermolecular forces. It flows easily and has low viscosity.
And so the movie misstates it a bit. The ethanol has pretty strong intermolecular forces, water very strong intermolecular forces. It's just that the glycerol, the molecules can actually kind of get tangled up in each other, and that causes the high viscosity. And so cohesive forces are the interactions between molecules in a bulk. Adhesive forces are interactions between, say, glass and water. And so it's kind of interesting. If the adhesive forces are stronger, then you'll increase the amount of interaction between the glass and the water. And so you'll get a concave meniscus. And so the reason this happens is the glass has some hydroxyl groups on it, and so it gives you a strong interaction with the water, and so it gives you a concave meniscus. Now, if the adhesive forces are weaker, then that would give you a convex meniscus. Now, the adhesive forces are also why geckos can walk in glass. And so you have intermolecular forces between the gecko's foot and the glass surface. Now this is actually a robot gecko. And so again, it's just intermolecular forces that enables it to walk in glass. And so when adhesive forces are larger than cohesive forces, you get a concave meniscus. When the cohesive forces are larger than adhesive, then you actually get a convex meniscus. It's also kind of interesting, if we put water on a surface, and if we have a strong interaction between the surface and the water, then we'll actually get a small angle. And so you see that this drop actually spread it out. Now here we have a much higher angle, and so that means the interaction between the surface and the water is being minimized. And so that means this is a bit hydrophobic. And so having a hydrophobic surface can be very helpful for many things. It repels water, which can actually keep the surface clean. And so if you're making like a solar cell or a wind turbine, you'd probably want a hydrophobic surface to keep those things clean, even though they're outside. Now what we'll see in this video is that we have a piece of glass. One side of the glass will have a hydrophobic surface, and so you'll get these droplets. The other side of the glass is going to be untreated, and so you'll see that the water spreads out on the surface. And so notice how the drops just roll right off the surface. This is the treated surface. And so there's different ways of treating a surface. You can use a coating. You can change the surface a number of different ways. Now this side is untreated, and you'll notice that the water doesn't bead up nicely. And so the water interaction between water and the glass is stronger, and so the water stays on the glass a bit. On the right one, I think, is the one that's treated. The left one is untreated. Once again, just intermolecular forces. We could also look at capillary actions in just intermolecular forces. You have the water can actually go up the paper because of strong adhesive forces between the water and the paper. You can actually use this to distinguish between different compounds based on their strength of the adhesive forces.
When a piece of paper is dipped in water, the water moves up the paper by capillary action. The attraction of the water to the surface of the solid paper allows the water to rise against the force of gravity.
And so it's kind of cool. If you get bored, you can actually make some grape Kool-Aid. Try this experiment with a paper towel, and you should actually see two different dyes will separate from the grape Kool-Aid. And so all intermolecular forces are electrostatic in origin, and so they follow Coulomb's law. So the force of attraction equals K, charge on particle 1, charge on particle 2, divided by distance squared. And so the larger the charge, the stronger attraction. The shorter the distance, the stronger the attraction. Also, please remember, the stronger attraction, the more stable; the stronger repulsion, the less stable. And so if we characterize the intermolecular forces as ion-ion, ion-dipole, dipole-dipole, dipole-induced dipole, induced dipole, induced dipole, we can actually look at the relative strengths. And so when we say dipole, think about a polar molecule. Polar molecules have dipole moments. When you say non-polar molecules, you can induce a dipole moment. And so when you see induced dipole, think about non-polar molecule. But even polar molecules will have induced dipole, induced dipole. Now, induced dipole is also referred to as London dispersion. I'll use those two terms interchangeably. And so ion-ion interaction is just interaction between ions, like in an ionic solid. Ion dipole is interaction between an ion and polar molecule. And so if you think about an ionic compound dissolving water, you're going to have an ion dipole interaction. So say sodium ions and a water molecule. Dipole-dipole interaction between two polar molecules. Dipole-induced dipole, you can imagine interaction between a polar molecule and a non-polar molecule. Induced dipole, also referred to as London dispersion, interaction between non-polar molecules. But you also have to remember that even polar molecules will have induced dipole interaction. And so if we can figure out the type of interaction that's present, we can actually typically figure out the relative strengths. And so, ion-ion is something on the order of 250 kilojoules per mole. Ion dipole is roughly 150. Hydrogen bonding is about 20 kilojoules per mole. And the dipole-induced dipole, and London dispersion is about 2. And so it's kind of depends on what exactly you're looking at. For dipole-dipole, it's only really important if you have, say, two compounds that have roughly the same mass. We'll see later that mass is good indication of London dispersion. And so if you have two compounds that have the same mass, they'll have about the same London dispersion. And so then if one is polar, they'll have a stronger intermolecular attraction than the nonpolar one because they'll have London dispersion and be polar. Also notice that for molecules, hydrogen bonding is the strongest interaction. And so hydrogen bonding is dipole-dipole interaction. It's just a very, very strong form of the dipole-dipole interaction. And so physical properties often are determined by intermolecular forces, but can be a little bit complex in actually relating the different physical properties to intermolecular forces. In general, the stronger intermolecular attraction, the more kinetic energy is needed to overcome the intermolecular attraction, the higher the melting point, higher the boiling point, and the lower the vapor pressure. I hope that was helpful.